Our next unit in the open channel hydraulics course will be the design of transitions in subcritical flow. This slide shows a subcritical wedge transition from a rectangular channel to a trapezoidal channel. These types of structures are fairly common where a lot of irrigated agriculture is present. So you can see here, if you look at the background, it's a desert, low rainfall area, and they have an irrigation canal which is concrete lined so that they will not use water. So notice there in the, I guess would be the upstream end here, is a rectangular channel, and then there's the wedge transition going into the trapezoidal channel. In the textbook by Roberson, Cassidy, and Chudry, they show three common types of transitions for subcritical flow. A is a cylinder quadrant, which you can see a cylinder wall is just simply wrapped around and matching up with the trapezoid. And then there's a wedge, which we just viewed, in which the rectangular channel angles into the trapezoid. The third type is what's called a warped wall, when you get into the actual transition and the wall is assumed to be continuously varying in slope. This type of transition is very easy to calculate, but extremely hard to build. So we're going to use the warped wall transition for calculations, and then we will put it into HEC-RAS to actually get a final sizing, for example, on a wedge transition. Preliminary hydraulic design of a subcritical transition involves ignoring friction loss. The depth of flow at each end of the transition is assumed to be known. The bottom elevation at the downstream end is to be determined. Notice this is very similar to the direct step method, and we're going to, by having a known elevation at each end. The energy equation and the contraction expansion loss equations are used, and a warped wall transition is assumed. If you look at a plan view of a warped wall transition, here you'll notice we are transitioning between two trapezoids. The trapezoidal channel on the left has 3-to-1 side slopes and a 14-foot bottom width. The trapezoidal channel on the right has a 10-foot bottom width and 1-to-1 side slopes. So you can see I've drawn 4 vertical lines in there indicating moving about a quarter away through the transition. At the end of the first 25%, the wall slope will have changed to 2.5 to 1. Going to halfway down the transition, the wall slope will change to 2 to 1. 3/4 of the way down the transition, the wall slope becomes 1.5 to 1. So you see it's continuously varying wall slope, which once again would be very difficult to build. The energy equation is applied at each end of the subcritical transition, and you've done this a number of times. And you'll notice that the H sub CE would be the loss associated with either the contraction or the expansion. That equation is shown on the bottom, and this equation you have also used frequently. In the historical approach to the design of the subcritical transition, start with steady state conditions and a known flow rate, the known upstream and downstream channel geometries, and then the transition geometry would be selected by the design engineer. And usually, because of the ease of calculations, that would be a warped wall transition. Then determine the depths at each end of the transition. Next, calculate the head loss through the transition using the expansion contraction equation. Now, what goes on here is that the energy loss, as it says, distribute the energy loss linearly over the length of the transition. So the energy loss will be uniformly consumed along the transition. What this means is that you'll be actually solving for the bottom elevation of the transition. Then you divide the length of the transition into cross sections and use the energy equation to determine the water surface elevation at each section. The last step is very essential because it's oftentimes the depths at each end are wrongly assumed, and as you put it into the calculations, you'll get numbers that just don't look right. So you have to examine the results to assure a good solution. There is a spreadsheet which has been prepared. It's called the Subcritical Transition Preliminary 1 Excel spreadsheet. For the following example, determine the vertical rise or drop which must be constructed in the subcritical warped wall transition, and by performing a preliminary analysis. The depth at each end of the transition is given. After you get the approximate length of the transition, use a length of 50 feet and use a bottom elevation of 100 feet at the upstream end of the transition. Here would be a profile view, which may not be correct in the transition, but on the left-hand side there's a trapezoid with a bottom lift of 12 feet, 3-to-1 side slopes, carrying a flow rate of 200 cubic feet per second. On the right side, there's a rectangular channel with a bottom width of 20 feet, obviously 0 side slopes, and also carrying 200 cubic feet per second. The design guidelines for subcritical transitions, either the convergence or the divergence angle, should be approximately 12.5 degrees. As you work through the spreadsheet, you should be able to complete this table. There is already a completed example within the spreadsheet, and it will be necessary for you to change the numbers. These are the solutions you should obtain when you work this example in that spreadsheet. You'll notice for this particular example, the transition has a smooth vertical step upward. So if we were actually constructing these channels along with the transition, this is a sketch of what the bottom profile would look like. This is the last slide in this presentation.